I don't think you need me to do the mean and standard deviation now. Is that safe to say we don't need to do the mean and standard deviation because I just did a modeling problem of that? Yes? No? Okay. I don't hear anything. Can I do another example? Okay, I can do it here. Same data from yesterday then. We'll use, this is the me shooting free throws, next 12 free throws, and I make 85% of them. So the things that we want to remember there is n equals 12. The probability that I make it or success is 0.85. Mean and standard deviation in this situation, that is going to be how many free throws should I make on average if I shoot 12? The mean of a binomial is super easy. It's one that if I had never started teaching you guys AP statistics, and you thought about it like Algebra 1 or Algebra 2 students, that's the one you could get. Mr. Wood shoots 12 free throws. He makes 85% of them. How many should he make out of 12? That's what that question's asking. It's just going to be 12 times 0.85. That's your average. That's your expected value. You should click with all the vocabulary that we have. I don't know what that comes out to be. Yeah, 10.2? Yeah. Okay. Sounds about right, if I was that good. I think it's probably the opposite. I make 15%. That's what I did. I took the time. All right. Standard deviation, that's now our mu x, what we call it. That's our expected value. We know when I shoot 12 free throws, I can't make 10.2. I can make 10, I can make 11, I can make 12, I can make 9, 8, 7, 6, but I can't make 10.2. The standard deviation, square root of n times p times 1 minus p. So it's the square root of 12 times 0.85 times 0.15. Okay. Yeah, that's out. What do we got? 1.237 there? Okay. Number 4, find the probability that Mr. Wood makes 7 or less. When I say 7 or less, that's the hard thing for students. What is it asking? Can I count the 7 or not? Is it acceptable here for me to count the 7? Yes. So including, that's up to and including. Hopefully you guys are realizing that that's probability that x is less than or equal to 7. And for full credit on this, what I want you to show me, this is what I need when you see a problem like this. Show me that that's the probability that x equals 0 plus the probability that x equals 1. Establish the pattern that you're doing. Then you can write plus dot 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 and then plus and show me the end of that pattern. Okay? What I'm showing you here is how to communicate without having to write everything out. Because yesterday I showed you how to plug into that formula. It's kind of a long formula. That's NC0 times P times 0.85, 0 times 0.15, 15 times. Right? Then you have to do that for all those values. I don't need to see that. I just need you to communicate that you know what you're looking for. And then write this. Show me the calculator language. They are starting to allow calculator language as methods of showing work. So if this was a problem in the AP exam, this is what you would need for full credit. Binom, CDF, and then give me 12, 0.85, 7. That shows you know what the calculator is telling you. Then you're going to use your calculator to do it. And then you're going to report that the probability that I make 7 or less free throws is, and whatever that decimal approximation is. 10239. People agree it's pretty low probability. 0.0239 is pretty low probability. And I'm talking about the probability that I make 7 or less. Does that probability make sense? Should it? And why?
Yeah, because
Yeah, how many should I make out of 12? 10.2. What's my standard deviation? 1.2. So let's just do some rough math. Do you agree that one standard deviation below gets me to 9? And then one standard deviation below that gets me to like 7 point something. Do we agree with that? So think about things in terms of standard deviations. One standard deviation, how much your data? 68. Two standard deviations, how much your data? 95. Isn't 7 below 2 standard deviations? Well, we know outside of 2 standard deviations on data, there's not a lot of data out there. So it should make sense to you that when I'm below 2 standard deviations, there's a rare probability in this situation that I should make 7 or less. So even though it's a low probability, it should match with what you know. And that's the next step that I want to challenge you guys to take statistically. Once you crunch numbers and analyze them, does your answer make sense in the context of the problem? Because I've seen students before in a problem like this get some answer of like 0.99. If it's true that I should make 10.2 and my standard deviation is 1.2, then the probability that I make 7 or less should not be 0.99. At no time whatsoever should that answer make sense in context. You see what I'm saying? And you guys have seen questions on your tests in this class. You'll see some questions that prompt you to that on your homework. Does that make sense to you? Explain. Does that match with what's supposed to be true? Explain. Because that's what they're looking for in the AP exam. They know your calculator does this. But what we want you to do is be able to say, does that make sense in the context of the problem, yes or no? Because is it valid? Okay? All right, normal curve. We can keep going on these, but I think you did a lot of those examples last night in your homework. So I'm not going to keep doing examples. Is it okay that I keep going on to the next topic? All right. So we'll leave that. We'll get into the next thing. This is going to be today. On tonight's homework assignment, you will see combinations of these. This is your next distribution that we're going to talk about. As I told you guys, hey, in this class, you're going to learn a ton of stuff. The calculator's going to do most of it. I showed you yesterday in those distributions. Notice that list was pretty long, right? What the key that you guys need to do to be successful is when to apply the right thing at the right place. And one of the hardest ones to tell the difference between is what's called the geometric distribution and the binomial distribution. They're really difficult to tell the difference. Okay? The best way that I can tell you the difference is geometric distributions are just imps. They're not pimps. Okay? Yesterday's binomials. You have to have the very first P, predetermined number of trials. I'm looking at the next 12 free throws that I shoot. I'm looking at the next 25 cars passing inspection. I'm looking at the next 13 people that walk through that door. That is a binomial. Predetermined number of trials, independent events, mutually exclusive, you make or you miss, you pass the inspection or you don't pass the inspection, you pass the test or you don't pass the test. Those are mutually exclusive, and then the probability is the same every time. Geometric and binomials share 3 of those properties. The key with geometric, there's no predetermined number of trials. Okay? There's no predetermined number of trials. Geometric, you keep going until the event happens. Okay? Geometric, you keep going until the event happens. Here's the really nice thing about geometrics. If you keep going until the event happens, there is only one tracing. For example, if we go to I make a free throw, I'm going to have to miss a free throw, miss a free throw, miss a free throw, miss a free throw, and then make one. That is a geometric probability. You keep going until the event happens. No predetermined number of trials. I'll show you what that looks like in just a sec. Good move? About that? I already told you guys this. You probably already had it down. Geometric random variable defined as x equals the number of trials until the first success is observed, including, this is another area that students kind of confuses them, including the success trial. That distribution is geometric. Again, binomial, geometric. Tomorrow we're going to look at normal distribution. Here's what it looks like. Suppose that 30% of students who drive onto campus at the university carry jumper cables. Your car has a dead battery. So you don't have jumper cables, so you decide to stop students who are coming into the parking lot and ask them if they have jumper cables. You want to know how many students you would need to stop before you find one with jumper cables. Okay? Find the probability of the fourth student having jumper cables. Okay? I will tell you that, yes, it is as easy as it seems. Not that easy. Because three things need to happen until you get to the fourth person. Okay? Remember, geometric means you go until it happens. Geometric goes until it happens. It needs to happen at what person? The fourth person. Which means, what needs to happen kind of overall? If our probability that somebody has jumper cables is 0.3. Oopsie. Probability of jumper cables is 0.3. Think about the tracing. We're looking at the fourth person. Doesn't that mean that the first person has to not have jumper cables? And the second person has to have not jumper cables? And the third one has not jumper cables, and then the fourth one does. Does that make sense? So what needs to happen in terms of if this is 0.7, and that's 0.7, and that's 0.7, and that's 0.3, it's an and event, this and this and this and this, right? You can see the patterning and how it's very similar to a binomial. But in many ways, I think it's easier. There's only one tracing that can happen. We don't have to worry about combinations. The answer to this problem is it's going to be 0.7 3 times and 0.3 once. Now your book uses kind of a tricky formula for it. How many people notice that they use the letter pi or the figure pi? That just means probability. That's what they use it for. So I don't like that they use pi. It does not mean 3.14 in your stats textbook.
Is it pi?
Yeah. No. Okay. It just means probability. Okay. So your book uses pi. It's not 3.14. What happens, or your formula for geometric, is basically this. 1 minus p, and that's going to be n minus 1, and then p once. That's basically what's happening. Let's say you're looking in the context of this one, you're looking for that fourth person to have jumper cables. So it's going to be 1 minus the probability of success times 4 minus 1 times the probability of success once. That's your generic formula. I think the book uses pi instead of p there. Okay? Like I said, geometric's easier. Up. Find the probability that 3 or fewer must be stopped, by the way. Let's look at this. What did we get? What did you guys get there? I don't know what that was. 0.0343. 0.1029.
Do it wrong, I swear. Romans 6 is
I don't know. I don't know what to do. I'm inclined to blame Ann, though. All right. Cal. You do have a geometric distribution on there. Notice that it's PDF and CDF again. PDF stands for what? C. Okay, let's go with C. What does the C mean?
cumulative.
Cumulative, up to and including. Okay. PDF means exactly that spot. Okay. So in this problem, we're looking at a geometric PDF, and it was what, 4 people? Is that right? And the probability was 0.3. I don't remember my language on this. I think it goes 4, 0.3. Okay. There's only 2 inputs, 4, and then the probability. I think that's the right input. Nope. Reverse it. I forget the input on that one. Notice the calculator, it doesn't really matter. It'll tell you if you don't do it in there right. Put the probability first, 0.3, and then the number of people you want. And then 0.1029. That's how you do that. Okay? C's coming, but there it is. Excuse me. It snuck up and then it left me. But we don't want that. Are we okay with geometric PDF? CDF is going to work the same way as the binomial did. CDF is up to and including. So find the probability that 3 or fewer must be stopped. If we're looking at that, it should make sense to you that that's the probability that x equals. Notice there's no zeros in this one. Okay? Think about the old one. If I was shooting free throws out of 12, there's a probability that I can miss all 12 of them. In geometrics, there's no zero. I have to stop somebody. They either have jumper cables or they don't. There's no probability that x equals 0. On these, it's the probability that x equals 1 plus the probability that x equals 2. 3 or fewer. Do I get to count 3 or not?
Yes.
Yes. Probability that x equals 3. Hopefully at this point, you're saying that is now a geometric CDF, and it's the probability first, which is 0.3, 3. That will sum, and I want to show you those calcs real quick. The probability that the first person has jumper cables, what is that? 0.3. The probability that the second person has jumper cables, isn't that 0.7 times 0.3? And the probability that the third person has jumper cables should be 0.7 times 0.7 times 0.3. They're going to sum all those up. Either the first person can have it, or the second person can have it, or the third person can have it. It's an OR situation, so they're going to add all 3 of them together. Do you see how this is blending what we did with the last chapter with this new stuff? ORs and ANDs and independence. Geometric CDF on that hopefully comes out to be 0.657. Okay. How about this one? This is tricky for students. Find the probability that more than 5 must be stopped. Mr. Wood, you said we keep going until we find jumper cables. What's that? Well, couldn't the 7th person have them and satisfy that? Couldn't the 8th person have it and satisfy that? Couldn't the 9th person? And theoretically, couldn't we have an infinite number of people that not have them? Now, it would be a very small, low probability. But that probability exists that I could go to 100 people and none of them have jumper cables. 100 isn't infinity. But I will tell you that even getting up to 100 is such a low probability, it's statistically insignificant. You're talking about micron, like numbers that probability is so rare it's not going to happen. How can we do this? Because I think you guys understand that it doesn't mean this is that it's not asking that the sixth person have it. Because the sixth person, the seventh person, the eighth person, the ninth person, the 10th person could have it.
1 minus the probability that up to 5 had it.
Okay, how many people agree with that? I am going to use what I know about complementary events. If I go probability that x is less than or equal to 5, plus the probability that x is greater than 5, doesn't that have to sum to 1? Does that make sense? And isn't this problem asking me the probability that x is greater than or equal to 5? Not equal to. Did I say equal to?
Yeah.
Oh, sorry. A probability that x is greater than 5. So, pre-algebra time, subtract that from both sides of the equation. And the probability that it will take more than 5 will be 1 minus the probability that it takes up to and including 5. Which for us, hopefully, 1 minus geometric, CDF, cumulative, and the probability is 0.3, and we want it to happen up to and including 5. And you can put that right into your calculator. 1 minus geometric CDF. What do we get, 0.1681 there? Anybody do that?
Yeah.
Is it 0.1681?
Yeah.
And again, you want to make sure that you're getting the setup correctly. The hard part for students is taking the probability statement and getting it into a correct thing that makes sense. Okay? So, most of the time, if 30% of the people have jumper cables, are you guys safe with me saying over 85% of the time, I'll get them less than 5. Or 5 or less, I should say it that way. Yeah. Over 85% of the time, I'll have to stop 5 or less people. Does that make sense? And I'm getting that 85% because it's 1 minus that. A little bit over 85.
Under 85.
Oh, yeah. Over 83%. Is that better? We good? Okay. All right. My dog Copper loves to play catch. Unfortunately, he's not very good. The probability that he catches the ball is only 10%. So that's equal to the number of tosses required until Copper catches the ball. And I want you guys to do these right now. Find the probability it takes exactly 2 for him to catch it. Find the probability it takes at least 4 for him to catch it. Find the probability it takes fewer than 5. And find the probability it take catch 5 out of the next 10. Okay? I want you guys to do those problems. And then actually, we're going to have you guys are going to have a work day for the remainder of class. Homework, and there will be a worksheet.